Right, moving on. Okay, we've got one of the amusement park style questions. So what you've got to think about in a question like this is, what can we determine from these sorts of information that are given to us. Now, the only possible thing we can think about is gravitational potential energy. So we're talking about energy changes, and we want to find the speed of the car at point B. So what do we know? We know m equals 1,000 kilos. We know the height of the platform is 20 meters. Now, we can calculate something from this because gravitational potential energy is mgh, so it is 1,000 times 10 times 20, so we have 200,000 joules. So this is the first part of what we need to do. Now, to find the velocity at that bottom point, so this is when all the kinetic energy at B has turned into let me start that again. All the gravitational potential energy at point A has turned into kinetic energy at point B. Now, I'm rushing a bit here and I'm starting to gabble on, but hopefully you get what I'm talking about. So we know that kinetic energy is a half mv squared. So again, rearranging this one, and I'm going to do this quite often because it is a very important rearranged form. It's not only useful in motion, we're also going to use it when we're doing light and matter later in the year. So it's an equation that you will benefit from being familiar with. So V equals the square root of 2 times the energy, which is 200,000, over the mass, which is 1,000, and we end up with the square root of 400, which is 20 meters per second. Again, a nice round figure suggests we're on the right track. Okay, from point A, the car travels up the slope to point C. At point C, it's in a vertical circle of radius 10 meters. At this point, the riders feel as if they have no weight. So we're thinking circular motion and apparent weightlessness are two concepts we need to think about here. So firstly, Rebecca says they are not actually weightless. Now, why is her statement correct or incorrect? Well, it is correct. They are experiencing apparent weightlessness because their actual weight force is mg. So that is what they're experiencing, the force on them is, but their apparent weight is mg minus ma. They're experiencing no reaction force, and so they feel that they have zero weight at that point. We're going to spend more time on these sorts of definitions and written ones, and you should also be having a look at the assessors' reports to get a feel for how they answer these. Now, moving on, what is the speed of the car at point C for the riders to feel as if they have no weight? Now, hopefully you're starting to see that this is a very common style of question, and that the key part of this is the acceleration is 10 meters per second squared. So the acceleration, the centripetal acceleration, must be the same as the acceleration due to gravity. So what else do we know about the situation? We know that the radius is 10 meters, and we're trying to find the speed that they're traveling at. So r equals 10 meters, v equals question mark. You'll know that a equals v squared over r. Rearranging this, v equals the square root of ra. So it is the square root of 10 times 10, which is, of course, 10. So, whoops, sorry, that jumped ahead a little bit. 10 meters per second is our answer. Okay, coming on to question 10 now. We have a helicopter which is 200 meters above the ground. Now, it's constant. Now, it is traveling at 10 meters per second in the horizontal, so I'm going to call that Vx. The pilot wants the package to land beside the hikers. Now, at what horizontal distance d from the hikers must the package be released from the helicopter? Now, the important thing in this question is the vertical time to fall. So it's again one of these questions where the first thing we think about is the vertical axis. Now it's also a pretty simple question because effectively all they're doing is dropping it out of the helicopter. We don't need to worry about the horizontal motion at all. All we are doing is thinking about how long it takes to fall. So what do we know? We know x equals 200. We want to find t. Now I know that when it starts to fall, its initial velocity is 0. And I know that the acceleration is 10 meters per second. So all I need to do is substitute this into an equation. So x equals ut plus a half at squared. Now this ut term disappears because u is 0. So what I'm left with is 20 equals a half 10t squared. When I rearrange this and solve it, I get t equals the square root of 200 over 5, so it is the square root of 40, which is 46.3. So that is the time required to the object for the object to fall 200 meters. What is the speed, now, actually, sorry, I haven't answered the question. Now, what is the horizontal distance from the hikers that the package must be released from the helicopter? So, what we've got to think about now is how far is the package going to travel in 6.3 seconds. Now, I've maybe not given myself quite enough room here. So we know that x equals vt. Now in this case the horizontal velocity was 10 meters per second. We've worked out a time of 6.3 seconds, so the distance horizontally is going to be 10 times 6.3, which gives us 63 meters. Okay, what is the speed with which the package then hits the ground? So this is now where we need to start to think about vectors. Now we know that it is traveling at 10 meters per second in that direction, and we need to think about what it is traveling in the y direction in order to work out the total speed, which is the hypotenuse of those two vectors. So all we've got to think about is the final speed. Now v equals u plus at. So what do we know? We know u is 0 meters per second, a is 10 meters per second, t is 6.3 seconds. So our final velocity is going to be 63 meters per second. And then all we've got to do is do our calculation here. So speed is going to be the square root of 10 squared plus 63 squared. So that's just our trig. And that is and we get 64. Now, it might seem a little bit weird that the horizontal component makes so little difference, but because of the how much bigger the vertical component is than the horizontal component, it just really sort of overpowers it. To draw this triangle accurately, if you think about your 10 meters per second like that, well, your vertical component is actually 6 and a bit times longer, so it's really more like that. And you can see that the hypotenuse here is not much bigger than the vertical component. Okay, so that is the end of the first part. Unfortunately, that has run to 20 minutes, so it's a little bit on the long side. I will upload the rest shortly.